We saw in the previous slide series that when a chemical reaction occurs, the molecules have to physically collide. And that was our kinetics part one presentation. Today, part two is asking a different question. We know chemicals have to collide, but how quickly can we get a chemical reaction once all these collisions are happening? How quickly can we get those chemical reactions to become completed, to reach equilibrium? And we therefore want to find out how can we affect the rate at which a reaction takes to get to completion. The key factors that are affecting the rates of a reaction are factors that increase the effectiveness of the collisions and the frequency that those collisions can take place. So the factors are temperature, the concentration and or pressure of the gases that are reacting, the physical state, liquid, solid, gas, and finally whether a catalyst is present. So we want to explore these four conditions and take a look at how they affect how quickly the reaction can go to completion. Now, temperature affects things almost always an increase in the rate. And the reason why is that at a higher temperature, the particles will collide more often, and the collisions themselves are more energetic. They hit with greater force, and both increasing the frequency as well as the amount of energy at the collision increases the success rate. What you see here is in blue, those collisions are effective. They're going to work. In the blue situation, at temperature number one, the blue, it's lower than temperature two, which is a higher temperature. And what you'll notice is as you go from temperature 1 to temperature 2, the overall effect is for the curve to shift right. And by shifting right, you increase the total number of individual molecules that will have enough energy for a successful collision. So you basically increasing your percentage of success. What about concentration as pressure? That's another way of causing a reaction to more quickly get to the equilibrium point. If you have a low concentration, the number of collisions are fewer. If you're able to increase the concentration of one or both reactants, then you have more frequent, more often collisions happening that will be more successful. Now, if you're increasing the concentration of the reactant, you can only increase the material that is involved in the reaction itself. You cannot, for example, if you have a reaction going on with sodium chloride, if you add or increase the concentration of iron, that doesn't have any effect on it because iron's not involved in that reaction. Now, pressure, if you increase the pressure of the chamber where the gaseous reactions are happening, you will be increasing that pressure only with material that is involved. Meaning, if oxygen is involved in a combustion reaction with methane, if you pump in nitrogen gas, even though the pressure went up, you're not going to increase the rate because nitrogen gas is not part of the reaction. So when we talk about changing the pressure to change the reaction rate, it must be using the gases that are involved in the reaction themselves. Now the third area that can affect reaction rates are the physical state. This is kind of cool. If you increase the surface area of the material that's reacting, then the rate will again increase. If, for example, you have a material that is a solid and you pulverize it and reduce it down to a fine powder, it more quickly will go through the process. Think about if you're adding ground up sugar to a cup of coffee, or if you're adding a lump of sugar, a sugar square. The powdered granular sugar will dissolve much faster than the solid sugar block, again because you have an increase in the surface area for the granular sugar. And that's nicely shown here. Now, what about the physical state? You got to think about this. Is kind of cool. If you have a clumping of a surface and you have hydrogen atoms trying to bombard the clump, it's not very good because they cannot access the material. However, if you split them into smaller bits, notice the hydrogen has access to many more of the items, and therefore it can happen much, much faster. Finally, what about catalysts? Catalysts are able to increase the rate of a chemical reaction. They increase the speed at which you can get to the equilibrium point. And it's important to realize that the catalyst does not get consumed. It does not get used up. The phrase is it participates in the chemical reaction, but it itself does not get consumed by it. And what it does is catalysts cause the um, um, molecules involved in the reaction to become properly oriented. Um, and it also, I gotta get rid of these things. It also allows for sometimes a different pathway to get there. It also allows for lower activation energy or energy required to successfully carry a reaction. By doing these things, proper orientation, perhaps even a new pathway or lower activation energy, they don't increase the number of collisions, but it increases the success rate that the collisions experience, and that will speed things up. What you see here is on the left, you have an uncatalyzed reaction. The area in blue is where the successes are. If you have a catalyzed, notice the curve didn't shift. What did shift was the line indicating the minimum amount of energy that's required. And by shifting the minimum energy to the left, you will have collisions that are going to be successful, whereas before in the uncatalyzed, they were not successful. Now, there's a limit when it comes to catalysts. You cannot add more and more catalyst and get the reaction rate to get infinitely better. What happens is there's a limit in which you saturate the system, and everything is tied up, and there's a limit to how much the rate can be modified um, by the catalysts that are being added. Okay? What is meant by zero order is that the catalyst itself does not get used to run any calculations, since it does not get consumed by the reaction itself. Now, the catalysts come really in two types. One is called a heterogeneous catalyst, and that's when the catalyst and the reactants are in different phases. The other possibility is, let's take a look first at the heterogeneous catalyst reaction. A Haber synthesis of ammonia is a very important reaction. It produces fertilizer. Another one is called the Oswald, and it produces nitric acid, which is used in very great volumes in other areas such as the making of fertilizer. And so the catalytic converter found in cars. All three of these are enormously powerful chemical tools that are used in today, and they involve a heterogeneous catalyst. In the case of a homogeneous catalyst, what that means is both the catalyst and the reactants are in the same phase, meaning they're both liquid or they're both gases. Acids and bases connect in this way. So let's take a look at a heterogeneous catalyst. First, what happens is the surface, or the solid in this case, is able to be absorbed onto a platinum surface. This particular one we're looking at is the one used in cars. This is a catalytic converter. And so you have carbon monoxide, nitrogen monoxide. They get absorbed under the surface of the platinum. It's important that this happens because it reduces the smog and air pollution. So what then happens is the carbon monoxide and nitrogen monoxide, they get arranged in a proper orientation. And that proper orientation is made possible because those gases are held on a solid surface, which is solid platinum. Well, wouldn't this work for copper? No. Copper does not have this effect on carbon monoxide or nitrogen monoxide. So you won't see copper as a catalyst, but platinum does work. And so what happens now is that the molecules that are sitting on the surface of the platinum, which is the catalyst, um, that orientation favors a chemical reaction. And what you get produced is carbon dioxide and nitrogen gas from the previous molecules. And these molecules are much less of a problem from a pollution standpoint. And because you now have created these new molecules, they're not held by the platinum anymore. In other words, by becoming CO2 and N2, the platinum is going to release them because there's not a chemical attraction for things. In the Haber process, what you have happening is the production of ammonia, and you use N2 gas and 3H2 gas to produce NH3, which is the ammonia. But to make that reaction favorable, what happens is we use a iron, aluminum oxide, and potassium oxide surface. That mixture alloy um, will bind the N2 and the H2 very effectively and promote the production of the ammonia. Notice again, the reactants are gases, but they sit down on a solid surface, which orients them better and makes the reaction therefore much more favorable. The Oswald process involves a surface that allows for the binding of the necessary material to make nitric acid. So in this case, you take ammonia, NH3, with oxygen, and it goes to nitrogen monoxide with water. That's the platinum catalyst. That solid surface promotes that. And then what happens is the nitrogen monoxide with oxygen produces the nitrogen dioxide. And then finally, that reacts with liquid water to produce the nitric acid. So those are three examples where you have a catalyst that is out of phase than the reactants. This is a look at, again, at a very important idea, which is the catalytic converter. We saw this reaction already. And what happens is the engine produces these wastes, incomplete carbon monoxide, CO, and NO. And what happens is it goes through the catalytic converter, which is the platinum we saw. Now, it's important to realize that the catalytic converter is not the muffler. The muffler is after, and that reduces the sound noise. But the catalytic converter allows for the conversion to CO2 and nitrogen gas, which is a much less damaging material. It should be noted that it was in the 60s when the air pollution became so debilitating for many people's health that one of the things that got legislated was that all cars have to have a catalytic converter. And that has made a huge impact on the pollution in America. There's an insight into the catalytic converter. One of the things about it is it's very porous. On the inside, almost looks like a honeycomb. And of course, that increases the surface area for the reaction to take place. Now, homogeneous catalysts are ones in the same phase. When you use aerosprays like hairspray that are under pressure, they use CFCs, which are chlorofluorocarbons. And what happens is that molecule, the CFC, is a catalyst that breaks down ozone, which is why we're punching holes in the ozone layer which is a problem because it blocks UV light. But it's the CFCs that is causing that breakdown because it acts as a catalyst. The CFC and the ozone are in the same phase. They're both gas. Enzymes are also homogeneous catalysts because they exist in the dissolved liquid state that they act upon. Enzymes are very important biologically. And what happens, as you can see here, is that the enzyme fits like a lock-in key to the reactant, which are the substrate, and it leads to the product. Notice that the enzyme itself does not get consumed. And oh yeah, baby, we got this. I think you're awesome. In case you weren't sure about that, absolutely, you are awesome.